Hi everyone, how are you? We'll start in a few minutes. Hi Josh. Hi sorry. How are you? Good.
I'm good. How are you?
I'm getting over a flu,
Ah,
but it's not too bad. I'm good now. Thanks. Nothing that Sudafed doesn't cure, I guess. Did you have a good Halloween?
yeah, I went out with family. We had a family party.
Oh yeah, that sounds fun. A lot of people have parties in my neighborhood. Well, good. I'm glad you enjoy your weekend.
Did you do anything?
It was my birthday on the 27th. I went to visit the old campus where I used to work at, which
Mm-hmm.
is College of the Desert. Some of my friends are still there, so they were playing golf at the college golf course, and then we went to go have some sushi in Palm Desert. It was kind of fun to see people that you used to work with, but yeah. That was kind of nice. And then I saw one of my old friends over the weekend with her daughter.
Oh,
So
that's pretty cool.
yeah.
Happy late birthday.
Oh, thank you. I just turned 44, so I'm a geezer. Once you hit 40, it's all downhill, right? They say. But I still feel like I'm 24 at heart, just to let you know. Yeah. So, oh, good. I'm glad you had fun over the weekend. We're almost done with the course. It's just a few more weeks and then you'll be in winter break. We do
Yeah.
have a holiday coming up. I know Veterans Day that will be on the Thursday. So that will be next week. Oh, Sam's here. Hi, Samantha.
Oh, hi, Professor.
Okay. Well, I posted some announcements. I do have access to practice exam if you are in, oh yeah, practice exam for programming under the Microsoft suite. I think after this year, they're going to discontinue that with Certiport. So, it's going to be available from now until January. I've been having it for the whole year, but nobody really wanted to make use of it. So I thought my students might be able to take advantage of it. If you're considering taking certification for any of those, let me know. I'll give you access to the practice test. You just need to install the Gmetrix on your system to access the practice test, and I'll give you the instruction for that. And I know that they have some IT cybersecurity degree career day things with Cal State San Bernardino and a couple of our employers. So if you're interested in those, check out the announcement for this week. I know I've been posting various things here and there, but yeah. So wanted to do Java, JavaScript, Python, C++, those things that will be good under the MTA, just to see how well you do on the practice test and see if you want to consider the certification. It's always good for resume. Okay. All right, we'll start in about a minute. So check out your notes for this week and your assignment. We're going to do cryptography this week, one of my favorites. Okay, so let me share screen while we wait for the rest. So this is the things that we're going to do this week. Also, we have a Veterans Day that's going to come up. Sorry, I'm going to pull up my crazy calendar real quick. Veterans Day that's going to come up on the 11th, so there will be no class on next Thursday. This Thursday, we do have class on the 4th. And then, so you will have that day off to celebrate Veterans Day. For those of you who are veterans, that will be a celebration. And so, and then mostly you don't have class on Friday. So that will be a long weekend next week, okay, the 11th. So keep in mind that we're not going to have lab that week, which just works out perfectly for us because in the next unit, we're going to talk about relations and also going a little bit on automata. So we'll just do like an online discussion for that. Okay. So with that said, we're going to touch on chapter 5 this week. We're going to come back to chapter 5. I wanted to save this for the end because I thought that it would be more applied to your project and also to really take a look at how to program cryptography. We're mostly going to hit Caesar cipher, which is going to be the one dimension of shifting character compared to 2 dimensions, which is Vigineer in your project. But the concept is pretty close, so you'll be able to apply. Okay. So in your notes this week, it touches on cryptography, and cryptography is very important. You use this every day, every time that you access online HTTPS website to pay your bills or to log into a website. It uses some form of encryption. Sometimes you would use encryption in documents where you would encrypt a file and be able to send that for forms. There are various types of encryption, and itself is just an individual course. But what we're going to look at this week is we're going to look at how we're going to be able to use the shift cipher, which is Caesar cipher, and then we are going to be able to program that in C++. So it's pretty fun. Okay, so now when you encrypt a file or use cryptography, you would apply an algorithm for specific type of cryptography. There are different types. And in cryptography, just to give you a little background, cryptography is really relying on the type of algorithm, the length of the cryptography, and the key length. And so there are some cryptography that has longer key length and some cryptography that have shorter key length. So for example, when you're using wireless or mobile devices, it would use AES, one of the strongest cryptography that's known to us today. And then there are times that we would use other form of cryptography. So to really give you the basic, we would talk about shift cipher, which is Caesar cipher. So the background behind this is Julius Caesar designed this cipher in a way that he wanted to deliver war tactics to his soldiers, his captains. So what he would do is he would tattoo the messages in cryptography, or it's encrypted, onto the scalp of a slave and send that individual to a certain region where they would be attacking. So that would be the stem in this particular type of ciphering. And so Caesar cipher is known as Caesar code or Caesar shift, but it is a form of shift cipher. Basically, it takes the alphabet and it moves, it shifts down a certain number of characters. And it is a type of substitution cipher. So we would replace a character by a shifted character in the alphabet. And so when you encrypt text, that will be plain text, and that will be applied to an algorithm, and then that will be, after it's encrypted, it would not be readable to whoever that's not intended to be the recipient. And so when you get the encrypted text, it would not be in plain text, it then be non-readable. Then when the recipient received that message, would then use a key to be able to decrypt it, and that key would apply the algorithm so that way we can decrypt the text and convert it back into plain text where we can read. Now, using the English alphabet, we would have 26 characters in our alphabet. And so an example of Caesar cipher is that if you start with the letter A, and if you wanted to shift it left a certain number of character, you would move back to Z and count left to that number of characters, like 3. And so the A would then be replaced by the shifted character. And so therefore it becomes a non-plain text. So for Vigineer cipher, I put a YouTube link there that explains Vigineer cipher, but the more modern approach to this, more of the recent application to this, is what we call the ROT13, which is rotate by 13 places, which is also a type of substitution cipher, where instead of 3 characters or 6 characters, it actually is being replaced by the 13th character shifted. So now, ROT13, of course, has a weakness because, you know, someone, if you're given a long enough time to really analyze the substitution cipher algorithm, you'll be able to decrypt the text, right? We will look for patterns. We will look for, you know, a certain type of characters that would show up and be able to reverse engineer it back. So ROT13 was used quite a bit in the 90s for various things like Usenet, which, you know, later on becomes what you see with news groups and things like that. So ROT13 is a common algorithm that you often see with substitution cipher. Okay, so let's take a look at the example. Let's say that we are going to shift every character by 3 places. If you're looking at the English alphabet, if you start with the letter A and end with the letter Z and not count all the symbols, okay, only 26 characters. If we start with A and we go 3 places, count 1, 2, 3. So the A is going to become the D, the B is going to become the E, and so on. So in this case, it's pretty easy to really guess what would be the shifted character after a while, right? You're going to start seeing a certain character that's going to show up. So if we're going to take a plain text phrase like discrete math, and we want to use Caesar cipher to encrypt that phrase, then when you start with a D, you're going to count 1, 2, 3. That will become a G. So the first letter that's a D is going to be shifted to a G. So it becomes a G here. The I shifted 3 places, 1, 2, 3. That lands on the L. So the second letter I becomes the L, and so on. Now, not all program would handle space or symbols like period, comma, and so on, because if we are using mod 26, we're only going to apply it to the 26 characters in our English alphabet. Okay, so just keep in mind that in this example, it does handle the space. White space is white space. But when you think about that, when you apply it to your project or your program, how do you handle space and how do you handle characters, right? How does the compiler see that as ASCII character? And that's important to think about when you work on your project. Okay. So as you look at the example, you can see how discrete math will become the non-plain text, the encrypted text here. And so when we look at the equation for our Caesar cipher, right? And then we would see that we would take the character, which is X, and we would add it with the shift key. So if I shift right 3 places, that will be 3. If I shift 6 places, K would be 6. And we have to mod it with 26 because there are 26 characters in the English alphabet. And so that simply is the equation for Caesar cipher. Okay. Any question? Sorry, I'm a little bit congested, so I'm finding this thing. Okay, so let's take a look at number 1. What we're gonna do with number 1. So based on the Caesar cipher, substitution cipher, encrypt the following messages by shifting 7 letters to the right. Okay, so we're gonna start with the letter C. If you count 7 places to its right, 1, 2, 3, 4, 5, 6, 7, the C becomes the J. Okay, so you can put that down. So we are manually shifting this, right? We don't have a ring, a Caesar ring where it can quickly use this. But when we program it into the computer, it's going to quickly do it for us. And then the O, if you look at the O here, if we count 7 places, 1, 2, 3, 4, 5, 6, 7, that lands on the V. So the O becomes the V. I just put it underneath so that way if that letter comes up again, I know which one to use. So I would put the V as the second letter. And then we would go to the next letter, which is the M. And so again, you count 7 places to its right, 2, 4, 6, 7, that lands on the T. So the M becomes the T. That's your third letter there. And then we would go to the P. So the P, and then again, count 7 places. Now, when you get to something like the T, okay? When you start with the T here and you need to shift it 7 places, then you go 1, 2, 3, 4, 5, 6. But wait a minute, that's the end of the alphabet. So we are going to go back to the beginning. It's going to loop back around. It's going to come back to A. That will be the 7th place. So the T will become the A. Okay. So it doesn't stop at Z. We're going to come back to the beginning of the alphabet and continue. So when we encrypt the two words computer science, we would have using 7 place. We rotate 7. That will be this. This is going to be the encrypted text. Now to decrypt, we would take this encrypted text and we would go in reverse, right? We would count to the left 7 places for every single character, and that will allow us to decrypt the text. So in that case, we would then subtract the 7 because we are moving left instead of moving right. In the ASCII, if you're looking at ASCII table, so let me pull up ASCII table so you can see. So if you simply look at ASCII table, right, upper letter and lowercase letter are treated differently. Okay, so the uppercase, the decimal value for this is 65. The lowercase letter, the decimal value for it is 97. And I know some of you are familiar with this. Most of you should be, right? You worked with ASCII before. So then as you go further, so let's say that if I need to shift, if I add in 7 as a decimal, right? I would go 1, 2, 3, 4, 5, 6, 7, right? So the 7 would then land on the later letter as we would add the 7 places to it. Now, if I'm decrypting and if I'm subtracting 7, I would take that value and subtract 7 from it. So because the computer would then take all the values and convert it into binary, it would operate the arithmetic in binary anyways. right? So then that's how you're able to do the rotation or the shift cipher, in that you would plus the K, which is going to be the place for the shift, the number value that you would shift to a certain character. Okay. All right. Any question as far as exercise 1A? So we just want to practice. So if we manually do this, right, we would understand the processes or the subtasks that we need to implement in our functions in order to really have that algorithm incorporated in our program to implement the algorithm. Then we would do the same thing again for B, keeping secrets. Okay. So if you start with the letter K, we're going to count 7 places to the right. 1, 2, 3, 4, 5, 6, 7. So the K becomes the R. So I put the R here. So the first letter is R. And there's a double E, so we just have to solve for it once, or actually 4 E's in this phrase. So the E, if we count 7 places, 1, 2, 3, 4, 5, 6, 7, that becomes the L. So the next 2 letter will be LL. And then the P, and you would do the same thing. So if you count that, the P becomes the W. And the I is going to be the P. And then the N is going to be U. So U here. And then RG is going to be the N. And then we will continue with S. S is going to land on Z for the shift. So Z. And then we already solved for E from earlier, so we can put that down. That's an L. And then C, if you count that, that will land on J. So J. And then R is going to be Y. And then E again, so we have an L again. And T is gonna, as we looked at that earlier, it's gonna come back to the A, so A. And then the S is right before the T, so it will be at the Z. So as you look at these, you can quickly solve for them and they're gonna get easier, right? As you would remember the shift. So in this case, we're shifting 7. And you can solve for C as I help you with A and B. You already got some of the letters noted here, so that should be easy. C is J, and then H, you just gotta count it 7 places and put the letter for your answer for the encrypted text. Any question? Piece of cake, right? Now, what you can also think about when you write your project is that if you want to keep everything uppercase, right? C++ does have the is upper function or the method that allows you to convert everything to uppercase. because remember the uppercase value is different than the lowercase value. So in the case the user put in the lowercase, if you want to convert it to all uppercase and then be able to apply for that, then you would be able to have the encrypted text in uppercase. Now, if you wanted to treat upper and lowercase differently, you have to apply the uppercase range and the lowercase range separately. And we'll touch on that when we talk about it in the lab. Because the ASCII values for A through Z is different in uppercase compared to ASCII value from A through Z in lowercase. Okay, the lower cases are higher. Okay. All right, any questions? So now, once we have the decryption or the encryption, we're gonna go to the decryption. Now we're gonna subtract, so we're gonna go left. Okay. So for 2, all you have to do is to take the encrypted text and convert it to the plain text. That's when we decrypt. So if we start with Z, we're going to count it 7 places to the left. 1, 2, 3, 4, 5, 6, 7. So the Z is going to become S. So we put S. And then the next letter is going to be B. So if we start here, we're going to count left, right? So 1, and then we're going to come back to Z. 2, 3, 4, 5, 6, and 7. So our B is going to be U. And if we already found A, then we would be able to get U too, right? Next to it. But B is going to be U. So U here. And then for our next letter is J and J. So J, count left 7 places. 1, 2, 3, 4, 5, 6, 7. So that's going to land on C. So we have C and C. And then the next one is L, S. We went from E to L earlier. So that is a given, but you can always count back, right? So from L, so that's going to land on E. So we would have the E. And then the Z, we're going to go back again 7 places. We already found the Z earlier. So that's going to give you S and S. And then the M, again, repeat the process. That's going to land on F. So you have F for M. And then the B, we found that from earlier, that's a U. And then the S is going to land on L. So that will give us successful. And then we can solve for the rest, and that should give you protection. Now you will find that there are a lot of different tools and websites that does solve for Caesar cipher, right? But manually doing this to help you understand the concept, so that way when you take this into programming, you would then think about how you would implement that with the alphabet. How are we going to move left? Are we going to increase or decrease? If we're encrypting, we're going to increase. Or decrypting, we're going to decrease. And then we're encrypting, we're going to increase. So as I solve A, you can work on B. And if you already put the letter there, you can just reference it real quick as we use the same value for the shift, the key. So the L, the U, the J, you solve for that already. So you just put that down. It's quick. Any question? Okay, so once we have our decrypted text, right, for B, then we can touch on encoding. Okay, so the next section in the notes is on encoding. And encoding is just a way that we would use numbers instead of letters. So we would encode or use the numbers as a replacement for those letters to be able to give us a certain value. Remember that your computer is a calculator. It converts everything to binary, whether you enter text or you enter a number, okay? And as you enter a number, that's treated as a string as well. So it's gonna then convert. So the common ways that we would see this is we would use the ASCII, which is American Standard Code of Information Interchange. And you can refer to the ASCII table like this. Okay. So if I type in the capital A, the computer will perceive it as a value. Okay. And here it gives you the octal value, the hexadecimal equivalent to A, and the decimal. Okay. And then the lowercase a, same thing, 97 for the decimal, 61 for the hex, and 141 for octal. Okay. So then this is just a schematic way for us to be able to represent a set of characters as values. So let's say that if we use the number from 0 to 25 as a system, right? We would then have 00 for A, 11 for B, 22 or 02 for C, 03 for D, and so on. And by the time we get to Z, that will be 25. So basically, we just systematically assign a value to a certain character, and that is an encoding process. And there are different type of encoding system, right? ASCII is one of them, UTF-8 is another. So keep in mind that applications use different encoding. So therefore, sometime when you are copy and pasting something from one application to the next, right? The symbols or certain characters don't interpret exactly because it uses different encoding system. For example, like from Adobe to, your IDE, right? Your Visual Studio, that might be different. So then we would see that we can simply convert our whole entire string to a group of values or numerical values, I should say. And so once you encode it, that means that we're going to take the letters and represent it as numbers. And when we decode it, we would take the letters or the numbers and then convert it back to the letters going the other way. It's kind of like what we've done with the shift with the Caesar cipher, but just this time with the numbers. So that brings us to the next exercise. Number 3. So I wanted to use the example in the book and we want to encode the string take on challenges to values, to numbers. It says encode the below messages using the provided table with the double digits from 00 to 25, as described in chapter 5. We will use 26 for space and 27 for period and 28 for comma. Okay, so we will start with T, and T is, if you look at T, that will be 19. So you put 19 for T, and I try to highlight it and color code it so you can see each of the word, right? So T is going to be 19. A is 00, so you put 00 after 19. K is 10, so we put 10 after 00. And E is 4, 0, 4, so that will give us take, is 19001004. And since we have a space and it tells us that we're going to treat space with 26, so we're going to add 26 for space, for white space. And then we're going to convert ON to numbers. So O is going to be 14 and N right next to it or in front of it will be 13. So 1413 for on. And then another space, 26. Then we do the next word challenges, starting with C, that will be 02. H will be 07. A is 00. Double L, so your L is 11, so you have 11 twice. And E we solved earlier, so that was 04. N we also saw earlier, so that's 13. G is going to be 06. 06 here. And E is 04. And lastly, your S is 18. So that's how you're able to apply encoding for the string take on challenges. Any question? Pretty easy, right? Okay, so then for B, you are going to solve. I did help you with the beginning part there. We're going to solve top secret and we're going to encode it from 00 to 25. So start with the T, put down the 2-digit for T, and then go to O to P and then the space. So I put down the top already. You just have to solve secret there. Okay, so make sure you complete that. And if puzzle is your thing, cryptography is great, right? It's about really, you know, solving that using an algorithm. So when you use your wireless router, right? When you authenticate to your wireless router using WPA2, that's a form of encryption. When you're accessing HTTPS to pay your bill or to check out your school information or financial aid or whatever it is, then that's also cryptography that you're using. That uses a public key. Most of the web stuff, so there are like two categories of cryptography. you have the stream, okay, that goes bit by bit. And then you have the chunk, which is like block size. And if you look further into crypto money and all of that, right, there's subdivision under that. So chain based with block encryption. So now most of the time web uses stream based cryptography because it's faster compared to if it needs to encrypt it by chunk, like data size, let's say, 4 bytes, or 256, and so on, 512, depending on the size, right? And that could take more resource and it will take time. So, we talked about time and space before, right? So in the application like that, you would see that we have to really look at what kind of result that we're looking for, and is it time sensitive, right? No user is going to wait minutes for a certain website to really authenticate them. Usually it's less than 50 seconds, or even lower than that for the user wait time. So what you want to do is you want to apply the appropriate cryptography, algorithm for that type of response. And that's important to really think about when you're looking at web applications or web integration with cryptography. Any question with 3A and B? Okay. So the next part, it talks about one-time pad or your OTP. And this is using Vernon cipher. This is another form of cryptography. Basically, it's just a different algorithm. So the plain text is going to combine by random key. And so this is known to be unbreakable because it's randomizing the key. And this was used in like World War II, where this was applied for intelligence purposes. It was also used by military for various reasons. So here it gives you a little bit of historical background on OTP. So the important things about an OTP, you do find this being applied in real world common, okay? So the key, what it is it's going to be as long as the message. So if your string has 200 characters and your key only has 3 characters, what that will do is it's gonna lengthen it by repeating those characters throughout to be matching with your message. Okay. So your key has to be at least as long as the message of the data. So if your data is 32-bit, then your key has to be matching. Second thing is that the key is truly random. It is not generated by a simple computer function. And we talked about pseudo-random before, right? We talked about true random and what would look like random. So if you're using a computer function, it would seed at a certain position. You have to consider, you have to implement time to really give it a true, like a randomized feel, right? So your key has to be truly random. Key and plain text are calculated using mod 10, which is for the digits 0 through 9, modular 6, which is for the letters, alphabet letters in English, that will be A through Z, and mod 2, which is for binary. So the systems that's applied. So in the case where the plain text would include digits and letters, right, it will be able to convert it. Key is only used once, so it's not recycled. So when you have a sender and the receiver, so if I send you an encrypted message, that key is only going to be used once. And after that, it is not usable. There should only be 2 copies of the key, one with the sender and one with the receiver. Now, this is different than public key encryption in that public key uses separate key, one to encrypt and one to decrypt. That's different. In the case where if you're using the same share key, right, that key, that matching key copies is only exists one time for one use, one with the sender and one with the receiver. So as you can see, different encryption uses different type of keys. And I know Khan Academy does a good job explaining OTP as well. So I put the link there for you in addition. So let's answer the next question since we're on that topic. For number 4, we are to describe the one-time pad ciphering method. It uses random key. The key is used as long as the message is sent and received. That means it doesn't get repeated. Sender and receiver hold the key. It's ideal for one-time use. Okay. I should change this. I'm sorry. I should put the key length is as long as the message. That makes more sense. No. Okay. Any questions on OTP? So with that, we do see some of the characteristics in OTP in Vigineer. Okay. You do see that Vigineer does lengthen the key to match the message length. That means the number of characters that you have in the message is going to repeat, or it's going to lengthen that key to be matching in the length of the message. Okay, so before we do number 5, I want to explain Vigineer as we are going to do a project on it. So Vigineer cipher was invented in 1586 as it gives you the historical background here. And it uses letters of the alphabet as primer, making the key that would be also letters. So that way we would be able to do the shift. Okay. So instead of using the value like what we've done with Caesar cipher, like 7 or 3, we're going to use the key letter to shift the character in the plain text. So the equation for that would be your encrypted text would be M plus K. K represents the key mod 26. And why are we modding 26? It's because this is the alphabet that we're using is the English alphabet, has 26 characters. And if we decrypt, we simply, again, very similar to Caesar cipher, we're going to subtract the key from the character from the encrypted text. We're going to subtract the key and be able to do the mod 26. And recall that each of the character in the key is a value to the computer. It's a number, right? We looked at the ASCII table. So if I have the key as ABC, ABC is represented as, it's encoded. So it would be, the computer sees it as a binary value either way. Okay. So here, what we would do is, here's a technique. To encrypt a letter, we would write the key underneath the plain text, take the plain text letter at the top and the key letter from on the left, and cross-section those two letters to cipher the text. In the first letter in our example, the T and the key X is going to give you the cipher Q. So you are going to use this chart, okay? And it is just a 2-dimension array of your alphabet. That's it, right? A through Z this way and A through Z this way. And we are going to start with the T. So if you go to T over here, okay, and the first letter of our key is going to be X, you're going to go down to X, okay? And that's going to land you on Q, okay? So you would take the letter, go across, and then take the key, go down, and cross-section it. And that's how you're going to come up with the encrypted text for Vigineer. So it's 2-dimension. Now, what happens when my key is really short? Like it has 3-4 letters. It's going to take that and it's going to repeat it, right, for the rest of the characters. Just like how we talked about OTP. Any question? Now, the downfall for Vigineer, I'm going to tell you, is that anytime you have an A, right, it is the same exact as the plain text, okay, in any form. So if the key is an A or if your plain text is an A, it's going to be itself. And then anytime that you have a Z, it's the opposite. It's a backward Z through. Okay. So, but the A you can see here, right? An A is an A and a B is B and so on. You see. Okay. So another thing that we want to learn is there's an Autokey cipher. And this is also named as autoclave cipher. This incorporates the message, the plain text, into the key. The key is generated from the message in some automated fashion, sometimes selecting the letters from the text, or more commonly by adding a short primer key to the front of the message. So what it does is it stuffed the original plain text with the key value, and that's how it's able to convert it. Okay, so that's a way that you can do an Autokey cipher. So there are 2 forms of it. There's the key Autokey and the text Autokey cipher. The key Autokey uses the previous members of the key stream to determine the next element of the key stream. The text Autokey uses the previous message text and determine the next element of the key stream. So in this one, we can say that we can probably implement recursive function here where it actually uses the previous, right? The previous output to be able to implement the next element, where the key Autokey, it uses the next one. So it's going to be the n+1, where it would be the next value in that array. So then you would see how different cipher algorithm would then be implemented. It's really interesting. I love this stuff. So, okay. All right, so let's touch on how to do Vigineer cipher for our exercise. So I want you to do this so you know how to program it. And you can always stretch this table a little bigger to see better. Okay, so we have the plain text, graduation is near, right? This is our string, no space, all in uppercase. And you have the key earns. So what happens is there are only 4 characters in the key. So what you have to do is you have to repeat that 4 character to lengthen it to match up with the length of your plain text. So I have 2, 4, 6, 8, 10, 12, 14, 16 characters. So you will have 4 urns. And we're going to go letter to letter, right? So you're going to go across to G and then come down to E, which gives you a K. Okay. Across to G, that's our plain text letter. And then go down to E, which is our key. And that's going to land you on K. And then you do the same thing for the R and the A. So go across to R and then go down to A. Guess what? Right? It's R. Like I said earlier, anytime you have the A in there, you're going to get the same as your plain text. And then again, we're going to start with the A for the third letter, and we're going to go down to R. It is R. So R. Just like what we said, anytime you have an A in either the key or the message, the plain text, you're going to get one of the letters there. Okay. Then the D, go across to D and then come down to N. That's going to give you Q. And then you do the same thing for U and the rest. So I started for U for the first few, and you can do the rest. A and A is easy. That should give you an A, right? And so on. Any question on Vigineer? So Vigineer is somewhat pretty easy to implement, right? And if you do have extra time on your project, I highly recommend looking at how you would treat upper lowercase, characters, space, as you know that the user would type in different things. So if you want to control that, you can also implement input validation. So all of that, just the conditions on what you want the user to input, and be clear on the instructions on how the program should be used. So if you're doing this particular program for your final project, right, you have to implement encryption and decryption, and you should make it fully functional in that we want to make sure that we treat upper lowercase symbols, characters, and so on. And keep in mind that you are going to be limited to what's used with ASCII, but you can elevate it by just implementing a different range for the symbols. Okay. So when we do the lab this week, you will be exposed to the Caesar cipher, which is the one dimension of it. And it's really easy, but you can definitely build out the Vigineer cipher for your project. And then for B, we would do the same thing for mask plain text. And we would take the word secrets as secrets for key, and we would repeat it, and we would lengthen it to as long as our string, our plain text. And then we would match letter to letter, and we would cross-section it. You can solve for B there. Any question? So the first part of this is to kind of introduce you to some of the basic cryptography algorithm. And then the second part of this is to walk you through the modular arithmetic. And mod is used for cryptography, right? As you see that we saw that in Caesar cipher and also in Vigineer. Any question with this exercise? No question. Okay, let's touch on the next part. Keep clicking that. Okay. So the book gives you a little bit more example, and it talks about how we would be able to do linear ciphers, in that we would do a mod 26 for the alphabet. We would take the plain text and we would be able to apply that plus the key. So when you have the cross section, so when you do an M is 5 and the K is 11, right? We want to be able to, we're going to shift to 11, and then the M is going to be 5. So all of that is going to convert to binary, and it would apply the arithmetic calculation. Okay. So when we use mod 29, that also represent additional characters beyond the alphabet, such as space, period, comma, and so on. Okay. So keep in mind that what if the alphabet has 128 ASCII characters? What would that be? So when we look at the ASCII table, okay, that you are limited to some of the symbols that are included in the ASCII table. For example, like the curly brace, the pipe, the tilde, and so on, in some of these. Okay, but there are additional symbols that might be beyond here. So if you're looking at other languages, right, we would then have beyond the 26 or beyond what we would see with this encoding system. Okay. All right. Next. Okay, so let's talk about mod function. And mod is used in cryptography. It also can be applied to calendars, clocks, randomization of numbers. So if you write a program to randomize your number, you often see mod. You can use it for hash tables. And so we saw that mod function is applied to our shift ciphers, or in general linear ciphers. So when you do a 17 mod 5, right, we would take 17 divided by 5. So that would give you, and division is just subtraction multiple times, right? We know that. So when we take 17 divided by 5, which gives us a quotient of 3 and a remainder of 2, so it would yield 2. And the remainder value is the output of mod function. Then we would take 8 mod 5. Again, we would take 8 divided by 5. That will give you 1 as a quotient, 3 as a remainder. So 3 is the output for that. 55 mod 5, that divides evenly. So 55 divided by 5 is 11 for the quotient, 0 as a remainder. So 0 is the output for that one. And for mod 5, since 4 is less than 5, if we take 4 divided by 5, we would get 0 as a quotient and 4 as a remainder. Okay. And then if we do 37 mod 17, 37 divided by 17, it's 2 as a quotient and 3 as a remainder. So the answer is 3. Well, how do we evaluate when there's a negative in the mix? Okay, so we're going to talk about that today. So here's an example. We would say that negative 17 mod 5. You're still going to get a 3, but when you look at this, we would first look at, right? That will be negative 4 times 5 plus 3 mod 5, right? Because this is going to give you a negative 20. And negative 20 is going to be plus 3, which is going to be 17. So let me put this in brackets so it's easier to interpret. So it's like doing this with this. But if I put it in bracket, then we would have to distribute, but you get what I mean. So that would be negative 20 plus 3, which is negative 17, and that represents the value A here in the front. And so that will give you, and the rest we just apply the mod 5. Okay. So the way that we write this expression is that we can use Q times N plus A mod 5, where A is going to be Q times N plus A mod 5. So if we want to represent this, we would be able to say negative 20, right? Which is negative 4 times 5 plus 3 mod 5. What about 8 right here, right? So if we break negative 8 down, that will be negative 2 times 5 plus 2. Okay. And then we just write that out as the expression mod 5. Okay. And then eventually you're going to see that the plus value here, that would represent what the answer would be, because that's the remainder. So on C, negative 55 mod 5 is 0. If we break that down, that will be negative 11 times 5 plus 0. And then that becomes mod 5, right? So the 0 is your answer there. And then negative 4, we can do negative 1 times 5 plus 1 mod 5. You see the pattern now? Very easy. Okay. All right, so that would be how we would use the negative. And that will be another example. Let's take the properties for mod. So if you have A mod n is equal to B mod n, then there's an integer k that is A minus B is equal to k times n. Second property, if you have A plus B mod n is going to be, we're using distribution law. So we would say A mod n plus B mod n mod n. Okay, so when you have something added in the parentheses, and if you mod it, you have to distribute it. Okay. And the same thing for the multiplication. So if you have A times B inside the parenthesis mod n, then we would have A mod n times B mod n mod n. And for the last property, when we have negative A mod n, you would take n minus A mod n. Okay, so make sure we remember these. Okay, so let's take a look at this example before we do the next exercise. When we have A plus B is equal to A plus B mod n, right? Then if you plug in numbers, you would also be able to see it better. So let's say A is 14, B is 17, and C is 5. So that would be 14 plus 17 mod 5. So when we write that out, we would expand it to 14 mod 5 plus 17 mod 5, right? Plus 17 mod 5 mod 5. We cannot forget the mod 5, okay? So if we take this part and find the output for that, 14 mod 5, that gives us 4, right? 17 mod 5, that gives us 2. And we can't forget the mod 5 that's hanging out there. So that gives us 6 mod 5, which is 1. Any question? Okay, that's the first example for the addition. Let's take a look at the multiplication. Similar, right? So we would say that A times B mod C is equal to A mod C times B mod C mod C. And so we would then expand it using the distribution law. So now let's plug some number in so it makes more sense. Let A equal to 4, B is equal to 7, and C is equal to 6. So if we have this, right, we can say that it would be 24 times 7 mod 6. And if we expand it, let's expand it. That will be 4 mod 6, right? I should put it in parentheses. 4 mod 6 times 7 mod 6. And then mod 6 on the outside. So 4 mod 6 is going to give us 4, right? Times 7 mod 6 is going to give us this one right here. Is going to give us 1. Okay, and then we got a mod 6 again. Which gives you 4. So either you go 28 mod 6 is going to give you 4, that should check. Or when you expand it and do the modular arithmetic, it should also give you 4. Okay. Question. All right, let's do the exercise now. First one's easy. 6. 80 mod 3. When you take 80 divided by 3, you have 26 as the quotient. Your remainder is 2. And you can use your calculator for this, right? Okay. So you use the, let's see. Sometimes. Yeah, the scientific mode got the mod right there for you. So the next one, B, you take 120 divided by 14. You should have an 8 as a remainder. And then for C, we would do 975 mod 2. That gives you 487 as a quotient with 1 as a remainder. So the answer is 1. And then for 61 divided by 3, you should get a 2 as a remainder. And then you can solve for E. Yes, I didn't do that one. So we simply do mod by taking the value divided by the mod value. And whatever the remainder would be the answer. Six is easy. Any question on 6? So make sure we find E. Now we are going to do the multiplication and the addition. Okay, so let's do the first one first. Okay, so for number 7A, it tells you that given A plus B mod C is A mod C plus B mod C mod C, then we would apply this format to here. So you have 15 plus 16 mod 7. Yes, you can take this, becomes 31, right? And then mod 7, you would also have the same result, of course. Okay, 31 mod 7 should give you 3. But if we break it down to this format, that will be 15 mod 7 plus, take this and distribute it with mod 7, which is this one, plus take the second term, 16, and then distribute it with mod 7. So 16 mod 7. And then we can't forget the mod 7 on the outside. So if you take 15 mod 7, that gives you 1, because 15 divided by 7 is 2 as a quotient with 1 a remainder. 16 mod 7, if you take 16 divided by 7, also 2 as a quotient and 2 as a remainder. So then we are down to 1 plus 2 mod 7, which gives you 3 mod 7 or 3. So this is just a longer way of doing it, but it lets you understand how we can get the same answer here as if we would take 31 and mod 7, right? You would also get 3. For B, we take 10 plus 29, simply that will be 39 mod 4. That should be 6 as a quotient with 3 as a remainder for sure. But we wanted to expand it. So we would do 10 mod 4, which is for this term, distributed with mod 4. Then plus 29 mod 4 for the second term. And then outside, we're going to multiply that by mod 4. So 10 mod 4, 10 divided by 4 gives you 2 as the quotient with 2 as a remainder. So 2 there. 29 mod 4, 29 divided by 4 is 7 times with 1 as a remainder. So 1. So 2 plus 1 gives you 3. And 3 mod 4 is 3. Because anything less than the mod value is itself. Okay. Any question with 7A and B? And you have to solve for C on your own, as I've shown you in A and B. Just like what we practiced. So make sure that we know how to do this, right? Not just to get the answer, but to be able to apply the concept and expanding and distributing it with the mod value. Okay. Any question with 7? Okay, question 8. So now, similar to what we've done with addition, we're going to go with multiplication for modulo. And the format I have provided here. So for 8A, we're going to solve 18 times 11 mod 5. You saw in the book example. So first, we're going to expand on the first term. So that's going to give you 18 mod 5 times 11 on the second term, mod 5. And again, we can't not forget the mod 5 on the outside. So 18 mod 5 gives us 3. 11 mod 5, right? Because 18 divided by 5 is 3 times. So 3 as a quotient with 3 as a remainder. 11 mod 5, 11 divided by 5 is 2 times, 2 as a quotient with 1 as a remainder. So 3 times 1 is going to give you 3 mod 5, which is 3. And yes, you can multiply this out and then operate the mod, which should also give you 3. Okay. B. For 8B, we're going to take 33 times 22 mod 4. And again, we are going to expand on the first term. So 33 mod 4 times the second term, 22 mod 4. And then we cannot forget the mod 4 on the outside. Then 33 mod 4, that is gonna take 33 divided by 4 is 8 times with 1 as a remainder. So you get a 1 for this right here. And then we would take 22 mod 4. 22 divided by 4 gives you 5 times with 2 as a remainder. So 2. So 1 times 2 is 2. So it becomes 2 mod 4, which is 2. And if you're fast, you can quickly solve for it. 15 mod 2, 27 mod 2. multiply it, mod 2 again, and you have the answer. So solve for C. Any question? Okay, so the next part, we're gonna handle exponent. Let's look at the example from the notes. So here it talks about these laws, the identity laws and distributive law and so on, right? And so when do you see exponent with modulo or modulus exponentation? When you're using RSA. If you ever use a Raspberry Pi or any kind of Linux OS and you want to use another system to connect to it, what we call a terminal, you're using an RSA key, which is a Vigenere algorithm. This is what's called the public key cryptography, and it uses some asymmetric key. So some cryptography uses the same key pair. Think of it like you have a house key and you make a duplicate of that key and you give it to your family, right? They use that same key to enter your house. That is when you have the symmetric key. That the matching key pair is symmetric. It's exactly the same. It has symmetry. The asymmetric key in RSA, it uses different keys. In PKI, one key is used to encrypt and the other key is used to decrypt. It uses a public and a private key. If the public key is used to encrypt, the private key is then used to decrypt. So in the case where if the key is captured, they cannot decrypt. So it is stronger in security. It is relatively slow. So therefore, when you see a lot of the faster algorithm, the faster encryption, it uses the symmetric key. So it's quicker. Okay. And I see that it's commonly used in authentication all the time. Okay. So RSA is quite common now. All right. So let's talk about computing powers using modulo. So we already learned about multiplication. So with mod, right? And if we take that to the exponent with the regular number, we would say that 2 to the 90th power is equal to 2 to the 50th times 2 to the 40th, right? You simply add the exponent when you multiply it this way. So when we have 2 to the 90th power mod 13, that simply is 2 to the 50th times 2 to the 40th mod 13. And as we've done in the past, we have expanded because this is simply a multiplication, right? So that becomes 2 to the 50th mod 13 times 2 to the 40th mod 13 mod 13. We solve for this to give us 4. We solve for this, the second term, which gives us 3. multiply it, you have 12, and then 12 mod 13 is 12. It's a lot easier than we thought, right? Pretty easy. If you understand the multiplication rule here, you would be able to apply it to the exponent rule here. Okay, so let's take a look at this example. So when we have 37 square mod 3, that would be expressed as 37 mod 3 squared, right? So if you mod this, take 37 mod 3, you would get a 1, and 1 squared is 1. So either way you solve it, you should still come up with the same answer. Now in the example B here, we have 115 to the 32nd power mod 7. So literally that would be writing as 115 mod 7, enclose that with the parentheses, raise it to the 32nd power. Or we can break it down. We can say that that could be 115 mod 7 to the 4th, and then raise everything to the 8th power, because when you do that, you multiply the exponent there, which gives you 32. Okay. And then we can break it down to also, when we simplify this, right, we would then get 4 mod 7 to the 8th, or 17 mod 7 to the 4th, or 2 mod 7 to the 4th, and then simply we would get back down to 2. So using modular multiplication, we would first look at the value before the mod and its exponent and trying to apply the multiplication rule. And that's how we will be able to break down the problem. Okay. So there are additional steps in the following example. All right, let's solve. Number 9. We have a to the m mod n is going to be a mod n, raise that to the m mod n. So for a, we have 4 to the 6 mod 3. We can write it as 4 to the 3rd mod 3 times 4 to the 3rd mod 3, right? By using the multiplication rule that we saw earlier. So that can be 4 times, if you do this, right, 4 to the 6, it can also be expressed as 4 times 4 times 4 times 4 times 4 mod 3. And if you're just looking at 4 mod 3, that will be 1. So 1 times 1 times 1 times 1 times 1 mod 3 is 1 mod 3, and it is 1. So there are many ways that we can actually express or find the outcome of 4 to the 6 mod 3. We can write it this way and then expand it out, or we can simply apply the exponent rule and write it this way and look at how each of the 4 mod 3 would be and use the exponent rule. So either way, you would still get the result of 1. So this is one method. Okay, I'm going to highlight that. This is another method. And this is another method. So you still get the same outcome either way. Please. Any question with 9A? All right, let's do B. This one is not too bad. So I'm gonna use the multiplication that we learned earlier on B. So 18 to the third mod 7. And so we would have 18 times 18, 8 times 18 mod 7, which can be written as 18 mod 7 times 18 mod 7 times 18 mod 7 mod 7. And if you solve for this, 18 mod 7 is a 4, because if you take 18 divided by 7, right, you have a 2 as a quotient with 4 as a remainder. So it will be 4 times 4 times 4 mod 7, which gives you 64 mod 7. And if you take 64 divided by 7, that will be 6 as a quotient with 1 as a remainder. So 1 is your answer. Take this out. Sorry. I don't know why I put the 4 there. Four times 4 times 4. Yep. So for C, I'll get you started, right? You can use this format, okay? Or what you can do is you can take a look at what 22 mod 9 is. What is 22 mod 9? If you take 22 divided by 9, right? That will be what? 2 times with the 4 remainder, right? And so you would take 4 times 4 times 4 mod 9. Okay. Or you can do it the long way, which is equals to, right? 22 mod 9 times 22 mod 9 times 22 mod 9 times 22 mod 9. That will be 4 times, then you're gonna mod 9. And then solve for that. So this, we would properly enclose this, so we would treat them separately. Oops. Then you just solve for that. Okay. Piece of cake. 4 times 4 times 4 times 4. And then mod 9. Any question? Okay. So check out the notes. Take a look at the project. Think about what you want to do. We already talked about graph last week. We touched on Vigineer this week. Okay. And if you wanted to do the blackjack, you can look at the blackjack criteria, which is the probability. We talked about that a while back. Okay. And if you don't like any of those cases, you can also come up with your own, but make sure that you approach me first, and I will take a look at whether it's an applicable case. Okay, it has to apply some kind of discrete structure concept. and you will have to do programming. Make sure that if we want to work in team, we sign up for team and work on that. Don't wait until the last minute where all the final exams are going to be due and it's going to be crazy. So just try to finish it as soon as you can and you don't have to worry about it. Okay, so I'm going to stop sharing, stop recording. Do you have any questions for me before we end? Okay, type your name into the chat.